mention that it was Professor Vishwanathan who brought me back to India, inducted me into the institute, and nominated me to the academy. So it was. So it's really wonderful to be introduced by him, and Ram, thanks for inviting me to do this. Actually, I was elected in 1996, and in 1997 I gave this induction lecture, or young fellow lecture, and this is the first time, I know, 21 years later, that I've been asked to come back and speak. So I'm very happy to be here. Life goes, a full circle, I guess. And and it so happened that I spoke about foundations of AI in some sense when I gave the induction lecture. And of course, it had a weird title. What I was speaking about was Leibniz actually had two concepts, right? Characteristica universalis, which was sort of symbolic language, which is a universal language, which is basically logic, and calculus ratiocinator, which was, arithmetic and computation. And Leibniz basically said these are two sides of the same coin. And computer science has largely absorbed the ratiocinator into the universalis characteristica. Right? So basically, computer science kind of worked with symbolism, with symbolic language, and so what a bunch of us tried to do in the 90s and the 80s was actually look how we might bring back computation through arithmetic, through geometry, and sort of work with languages, symbolism in a different way. And that's why it's called eating sauerkraut with chopsticks, because you're solving symbolic problems using arithmetic or using geometric ideas. So that was the book that came out a little bit after I was inducted, called Optimization Methods for Logical Inference. And these people, I did want to point out, John, of course, was my collaborator right through, and we wrote the book together. Bob Jaroslaw actually was the one who sort of asked us to work on this program. Unfortunately, he didn't live to see it fulfilled. And Jean-Louis Lassalle was more from the programming languages side, the logic side, and he was trying to embed arithmetic through constrained logic programming languages at IBM. And I spent 5 years in the summers working with Jean-Louis. So these were all sort of laying down the foundations of artificial intelligence of a certain kind. And we'll talk about other kinds of artificial intelligence. But the whole idea of artificial intelligence actually goes back to Alan Turing. And this is the same time I gave that lecture, we also brought out a special issue of Resonance. And that's, it was not Subhankar though, it was Prema Iyer, who used to do the illustrations. I was an editor for the first 5 years of Resonance. And when Professor Mukunda was heading it up, and so that was a sketch of Alan Turing, and I had talked about the Turing test, which was called the Imitation Game. So, a man or a human in one room, a computer in another, and a teletype, and if you can't make out which is which, then the machine has achieved artificial intelligence. And that was Alan Turing's idea of how to, define how to answer the question, can machines think? He didn't want to get into all kinds of philosophical questions. He said, here's a simple test, let's set it up, right? And sure enough, people worked hard on making machines that could play chess. And around the same time, again, as I was inducted, I guess Kasparov was beaten squarely by Deep Thought, right? Which was the IBM computer. And incidentally, Kasparov now is gone to Oxford as a professor at a very nice sounding institute. It's called the Future of Humanity. I was telling Ram earlier in the tea break that this is the kind of thing that the academy can do. If you have resources, maybe create something that is like an institute that's looking at the future of humanity. And he's, of course, now trying to see how machines and man can work together instead of competing. Right? And I think that's he has a recent book out called Deep Thinking, which is fun to read. Also, it tells you the history of that whole chess tournament and, and so on. Right? So this is the real talk, Sciences of the Artificial, Promise and Reality. I first called it Hype and Reality, and then I switched it to Promise and Reality. But we'll also talk a little bit about the hype. And I've been collaborating with a computational ecologist, and his name is also on there. And the interesting thing about artificial intelligence is that it's not one of those things that's that's in the buzz that is confusing the public. It's actually confusing scientists as well, right? So I think it's really worthwhile to think about a workshop that the Academy runs on AI and bring multidisciplinary people together to think a little bit more about what is artificial intelligence and what it means, because people are getting frightened, right? Even when Kasparov was beaten, some people jumped off bridges because they said, the machines are going to take over, these robots are going to destroy us, and so on. And so, there's some reality to the threats, okay, and there's a lot of hype as well. So we just need to probably, again, scientists would be the best people to sort of negotiate this whole situation. So how does this all relate back to logic and formalisms and Leibniz and so on? So John McCarthy in the 50s, early 50s, actually was the one who coined the name artificial intelligence. And what he said was that, the Turing test, or the test of intelligence, can only be solved by a logical machine, right? And he said, and he sort of pushed the whole quest for, intelligent machines towards building logical machines, right? And he also came up with this name to differentiate from what Norbert Wiener and others were working on, which was called intelligent systems, cybernetics, and which included fields like, operations research, which was the discipline that I was trained in, and so on. So McCarthy wanted to differentiate. So he coined artificial intelligence as the name. But he was actually being very, very specific. He was saying that he wants to create a machine in the image of a man, right? And this machine will have to be a logic engine, right? And I think he was probably mistaken on both counts, right? There is no reason why intelligent machines have to imitate man. And, and there's no reason that they only have to be located within the logical formalism. Okay? So I think the field has actually moved far away from that idea, but the name stays, right? So I think these were all, small, subtle things that I thought, this is the kind of things that I think we need to get the public to be a little more aware of, and the scientific community. So so each one was coming up with a different name. I think Herbert Simon, who at that time was at the University of Chicago, came up with the idea of the sciences of the artificial. And basically what he was pointing out was that intelligent systems, problem solving, all of these are actually looking at more at man-made systems. And, and we need to actually think of a new language for looking at these sciences, these problems, as opposed to the natural sciences which we're looking at nature. right? And so Herbert Simon, of course, then won the Nobel Prize and then moved to Carnegie Mellon. And at Carnegie Mellon, he kind of set up the whole artificial intelligence community and program and so on. It became one of the great centers in this field. But late at night. But anyway, that's sort of the timeline of what we just talked about. And of course, now we are coming into a very special era, and I'll try to give some sense of why that is so, right? So this is a curve very compressed in time, which talks about some parameters of human development. Come up, I mean, it's an economist sort of perspective, but as you can see, it is only with the start of industrialization that the curve starts bending significantly. And, we are now at a very vertical phase of this curve. And that is now being called Industry 4.0, the cognitive era, etc. Right? And of course, that is a slightly facetious comment that numerically most of human history was boring, but from the point of view of development, it's really accelerated in a huge way with technology. So the question of this vertical sort of development, has in technology terms has been sometimes described as a singularity, and sort of in some ways singularities create accelerations, and it becomes very hard to predict what is going to happen. Right? From a mathematical point of view, we know that a singularity is, in some sense, not really something that you can work with. You can resolve singularities in certain ways, but you can't actually use them in a very specific way to predict. But and Ray Kurzweil, who talks about singularities and has set up the Singularity University and so on, basically, is pointing out that things are happening much faster than we thought, right? If somebody had asked me when would we have automated vehicles, cars that could drive themselves, I would have said 2025, right? But it's come a few years earlier. Right? So I think these are there is something going on, and people are calling it singularity. But by and large, I think one has to factor in this whole hype factor, I think, which is with technology, the world has become a marketing machine, right? So in some sense, any breakthrough is then hyped incredibly. So everybody thinks it's around the corner, and it takes a long time to actually happen, right? The internet, that we all are now so addicted to, I think in 1993 or 1990 when the internet was first announced, and but it Google's IPO was when it really happened, right? Which was like 2004 or somewhere around there. So it takes a while for it to really become real. But and according to Kurzweil, if you go back to the John McCarthy concept of an intelligent machine passing the Turing test, he thinks it will happen only in 2029, which I should keep a watch on time, but 2029, which is still about 10 years away. But there are various versions of the Turing test that people keep saying have actually been passed by a machine, but it's there's one particular Turing test which is really interesting. They actually give an award to the human who wins as being the most human, right? So I think these are all really interesting sort of caveats. But just like scientists often are faced with Wigner's statement that the unreasonable effectiveness of mathematics in the natural sciences, is a startling sort of thing. I think we should now start thinking that there is an unreasonable effectiveness of machine learning in the sciences of the artificial, right? And I'll try to give a sort of balanced view of this, but let's so let me actually lay out the negatives first before talking about some of the things that it's achieving. Well, first of all, this machine learning business is again putting AI onto the same problem that McCarthy put it onto, which is you're saying it's a one-trick pony, and that has its problems. Also, this machine learning stuff is black boxes. So you basically it breaks when you change the problem, right? The third, yeah, and that's of course what is also said there, that a black box cannot explain why a solution found is good or why a prediction makes sense. So you become extremely dependent on this black box, and very difficult to sort of work with that. Now let me talk about the amazing things that machine learning is actually accomplishing, and maybe also define machine learning a little bit for the audience here. But I was in China about 3 weeks back, and of course, as you know, the Chinese government has decided that it's going to be, the world power in machine learning by 2030. And part of the reason for that is Andrew from Stanford University, who was the founder of Coursera, actually went to China and set up Baidu, right? He set up the machine learning group at Baidu, and so China is now sort of well positioned to take a dominant position. And Geoffrey Hinton is, of course, the person who's actually built the apparatus of machine learning in some sense, particularly deep learning, and we'll look at what all that means. So if China announces something, and by the way, I walked around this hospital, the Peking University Hospital, and the levels of automation and artificial intelligence in there, is sort of stunning, right? There are robots roving around which can negotiate elevators, sense how many people are in them, only stop the elevator if there's enough room for the robot to get in, go to the ward, and and then deliver medicines, and all kinds of safety precautions are all built in, and it's pretty incredible. And of course, China is thinking that AI can actually help in the whole healthcare delivery, which of course could be very useful for us as well. Right? Now, clearly, when China announces something, India has to follow suit. So Niti Aayog releases national strategy on artificial intelligence and identifies the focus areas, and we don't have a Geoffrey Hinton or an Andrew, so we have to make do with Mr. Amitabh Kant as being sort of the leader of the AI movement, right? So that's fine. I think at least we've woken up. I think something might come of this, so I think I think there's a lot of excitement about AI in India now. Within the government circles, you keep getting called for DBT meetings where they want to know what we should do with genomics and AI, and, because everything is going to be driven by AI, and so I just I think we need to again understand what can be done and what can't be done, and I just wanted to point out that back in 2006, I think we were in a pretty good position in this whole machine learning business. Actually, the team at IISc from computer science won the World Cup of data mining, which is the KDD Cup. And of course, our team at Strand were the runners-up in the adult category. So we were actually pretty much there at the cutting edge of machine learning. But since then, I think in 10 years, there's been some extraordinary progress, mainly due to progress in hardware. So we'll talk a little bit about that. This was also just some work done at CSA in the 90s by Satyakirti, Vinay Vishwanath, and myself, and our students. And at that time, that was the world's largest hopfield net, recursive hopfield net, that had been optimally trained. It was a 30 by 30 grid, which was basically 900 times 900 sort of hopfield net, which had about 40,000 interconnects. So there were 40,000 parameters that had to be tuned, and we proved that it was optimally trained, right? Mathematically, and so that was a nice result. But today, neural networks are being trained with hundreds of millions of parameters, and that's the difference. And by the way, this problem took us, I think, about 29 days of computation to actually prove that it was optimal, and then we had to run it a second time to make sure we were right. So it on some fun workstation or something like that. Now let's talk a little bit about artificial neural networks, and I'll run through a very quick tutorial of what this deep learning is about. It all starts off with this idea of the neuron, and I think everybody is familiar with that. I guess a single neuron sort of signal was the sigmoidal sort of structure was even known very early on as a perceptron by Minsky and Papert and various people who were working on these. And basically, you want to search for a curve that can separate classified, right? So if you have two neurons and one layer, you can start getting some sort of classification. If you go to three neurons and one layer, you actually can get that curve which separates. So these are nonlinear regressions which can classify. How slightly harder example. So the two colors have to be separated, and now they're in a spiral pattern, right? So if you give in to four neurons, you don't do very well. If you go to 8 neurons, it's still struggling. But when you add another layer and stay with 8 neurons, you get the separation. So basically, you're increasing the parameter space, and as you're increasing this parameter space, you're able to do the classification better. That's really all there is to this. But of course, now when you want to do facial recognition and very high complexity classification tasks, the problem becomes much harder. And can you recognize those two faces? If you can, you've achieved that perfect yin-yang, right? That Shabana talked about yesterday. But I think, a lot of people have difficulty recognizing faces when they're oriented in a different way and so on. And so that's, of course, Angelina Jolie and Rekha. When DeepFace was done at Facebook, this was a 9-layer deep neural network with 120 million parameters. They used 4 million facial images, and they got an accuracy of 97 points. So now, once that network has been created, you can recognize faces in the crowd. You can basically use it for all kinds of surveillance or all kinds of tasks, right? So what is the lesson from this? There was that old handcrafted intelligence versus deep learned intelligence. Deep learned intelligence seems to be more machine driven. Now, how is it that we can actually tune to 120 parameters? Well, it's because of Moore's law, right? And there's hardware now that can run these algorithms because of GPUs and various types of highly parallel processing engines that have been created. So your propagation algorithms, algorithms, and optimization problems, the conjugate gradient methods that need to be run to solve these problems can be run extremely fast. And so computer hardware has reached that capacity. But you also need huge training sets. And unless you have well curated training sets, you're not going to be able to build useful classifiers. Right? And so our bigger problem in the country is that we are lousy at archival. Right? We people hate to archive, they hate to share their data, and we have done precious little in putting together good data. And of course, there's a lot to learn from the Brits, but they were running colonies, and so they needed to be good at archival, right? And so they developed that culture, right? But we're always proud of our oral cultures and so on. So we've just not, our library science has not evolved into information science, and I think that's a big challenge that we have as a society. If we want to be part of this game, we have to learn to be better archivists, right? So I've been involved in this whole field of the genomic revolution for the last almost 20 years now. So this whole area of next-gen sequencing has really been explosive, right? And so just as Moore's law has been doubling capacity in compute in electronics and at once every 18 months, I think in genomics now the doubling is happening, or the halving of cost is happening at an even more accelerated rate. We are moving actually at the square of Moore's law. Right? And the cost per genome now internally at Illumina is, for a whole genome, is $100. Right? They charge us $1,300 or something like that. So they're the world's most profitable company, right? That's all you can say, because they're operating as a monopoly. But BGI has come up, Beijing Genomics, is now offering at $750. So there's going to be a price war, which is good for all of us. And just to give you a sense, Moore's law has been operating since 1958, doubling every 18 months. And so there's been a speed up factor of 2 raised to the power 40. While genomics has been doubling a little bit faster since 2007, when Shankar and that group at Cambridge came up with the Solexa machine, which became Illumina. And that now is, we have now reached the second half of the chessboard. So it's like 2 to the 32 times. So this is also accelerating very well. So what we realized in the group at Strand was that we need to actually build the technology that would scale with the whole field of genomics. So what we did was we actually built a lot of the numerical engines and the data analytics engines that were needed to deal with, say, 200 gigabytes of data that comes off of a read of a whole genome sequence. And there we do use GPUs and all of this new hardware. And natural language processing, we actually created, so IBM talks a lot about Watson. I think Strand created Grammatica in 2005, and we've been reading all of PubMed and all of Medline and extracting using a natural language processing engine. So it actually extracts from text, using, these are, finite state machine representations of the grammar of a verb, right? So there's actually, we've coded all the rules of English grammar, and we're able to read these journal articles and extract information. So from a sentence like that, you can extract kind of an indicative, um, interaction network, and then you build up these networks, and you can get to pathways, right? So this is how Strand has been internally building up its stack, and today we are able to report and interpret on clinical data that comes out of sequencing in a very efficient way because of that, and that is allowing us to do these tests and deliver these tests today at costs at about 1/10 of what the West charges for similar tests. So automation can be extremely helpful and stuff like this. Incidentally, Strand is the first academic spin-off in India from an academic institution, and IISc is still a shareholder in Strand. So we're very happy to to point that out. And Strand has now become, I think, one of the larger diagnostic companies in India, and we do about 1 million plus tests a year. Not all of them are genome sequencing. About maybe 5,000 to 6,000 tests of those are genome sequencing tests, but we also do a lot of other diagnostic tests. Just wanted to mention that a couple of other areas that would be ripe for AI is algorithmic trading. Deep learning is a big part of that. David Shaw built the hedge fund, the D. Shaw Fund. Jim Simons, the mathematician from Stony Brook, built Renaissance Technologies, and today you have all these Simons centers, right? That ICTS and NCBS and so on have, and those are all from the foundation that Jim Simons has built, and they basically use all these quantitative methods to trade on the stock market. And a few of us are just building something like that for the Indian stock market. So we're just starting that. It's just about a few months old now. I've also been involved in digital heritage. It's a big DST project. We've kind of captured the monuments and the intangible heritage of Hampi. And it's a group of over 100 researchers from around the country who've been involved in this project. There's a book coming out, and I think I was just got a message saying that it'll be in March, will be the book release in Delhi. But the interesting thing is digital heritage as a science is also evolving. I think as we move into this cognitive era, there's going to be deep learning based pattern classification and feature extraction, and questions of historicity. For example, in Hampi, we ran into temple mural paintings, ceiling paintings, which the historicity of those are not known. There's a claim that it is in the 1500s, but the styles look like it was painted over. It's probably 1800s. Can we actually resolve some of these historicity questions using these machine learning techniques? And then it can go on. It can get ontologies of heritage, again created through semi-automated or automated mechanisms, and you could also have robots as artists painting in different genres, right? So my last slide is actually the use of such a robot, and it's also my acknowledgement slide. The acknowledgement is to my mentor, who's Professor Rodam Narasimha, who has always told us that this strength in computation, which he calls computational positivism, is something that is a very Indian strength, and we should sort of build on that. And so that's the mentor, and these are my fellow culprits. We've been on this. We ran a lab together in the computer science department at ISC. We went on this entrepreneurial journey together. Just to introduce them, the impressionist version is, we are a gang of four, right? But the sort of photographic version is Vinay Vishwanath, theoretical computer scientist, but what is he building? Today he has an autonomous vehicle which can called the Sherpa, and Ati Motors is the company, and that Sherpa can carry 1 ton of load, and it is already now running around in ISC and has been on go-kart tracks and so on. This can actually be used for transport within sort of a factory or a campus and so on. So Ati Motors is what he does. Manohar is now at the Microsoft Research. He runs the virtual reality team there, and they're doing all kinds of neat experiments. And Ramesh Hariharan on the extreme right has relieved me of the burden of running Strand. So he's my successor there, and I've returned to the institute, as Envy pointed out. And I just want to end with 2 quick comments. I think one is that, as I mentioned earlier, I think the academy would do well to actually create a dialogue or a workshop where we actually need to realize that the public dialogue right now, which is focusing very much on this narrow subset of industry and academia, it perhaps is blinding us to opportunities and challenges that we need to take on in a much broader sense. AI is artificial intelligence. IA is intelligence augmentation, where you're sort of helping the human perform better. And intelligence infrastructure is what we otherwise call cyber physical systems. And so all of these need to be thought of in unison. And I think not AI doesn't have to have such a special place. I think we all need to make that happen. And then finally, I just wanted to end, in my mind, this might be the last time I get to address the academy. So I did want to point out that I think we have missed the boat in many ways in actually creating a think tank that can advise society and advise the government on very topical issues, right? And everyone knows about the Manhattan Project, but after the Manhattan Project ended, the US didn't stop there, right? They created something called the JSONs. And initially, of course, it was physicists, but then they quickly realized that they had to admit others in if they wanted to be relevant. And even today, the JSONs actually puts out reports on technologies, emerging ideas, the future of humanity, and these are actually driving policy, and these reports become public in various ways after a few years. Initially, they're held strategically, and then they become public. And I think our academies have an opportunity to play that role. These are about 100 individuals who meet and prepare these notes. And I've read the note on genomics. They knew 5 years ahead of everybody else what exactly was going to happen, right? And that was, and I think this is again a thought that perhaps the academy can take forward. Thank you.